Umang Mathur on verification of uninterpreted programs.
Hi, I am Umang Mathur, and I'm going to be talking about verification of uninterpreted programs and a decidability result that we have in this context. And this is joint work with Professor Madhusudan Parthasarthi and Professor Mahesh Vishwanathan. And all the three of us are at University of Illinois. So let me start by stating an obvious observation. Program verification is an undecidable problem. By program verification here, I mean completely automatic verification that is without the use of any manual annotation in terms of loop invariants or contracts. So while there are decidable classes that are known here, most of them are either programs that work on finite domains, so things like Boolean programs, or things like Petri nets, which are things like the increment counters or decrement counters, but cannot really check for zero, and therefore are not natural models of programs. So when it comes to verification for programs over infinite domains, it is really an undecidable problem, and practical verification always requires some manual annotations in terms of loop invariants. This talk is about uninterpreted programs. And by that I mean the functions and the constants and the predicates in your program are completely uninterpreted. And these interpretations are given by data models. And we say that these programs satisfy a specification if the specification holds in all these data models. So let me summarize the contributions of the paper. The first result we have is that verification of uninterpreted programs is an undecidable problem. And the main contribution of the paper is this class called coherent programs, or in general k-coherent programs, that admit decidable verification. In fact, to the best of our knowledge, it is the first natural class of programs that work over infinite domains and yet admit decidable verification. We show that these programs are decidable even in the presence of recursive function calls. So when you don't have recursion, these programs are PSPACE complete. And in the presence of recursive function calls, verification is X-prime complete. We also show that we also give a maximal decidability kind of result that says that if you relax certain assumptions about coherence, you sort of immediately give rise to undecidable verification. So the syntax of these programs is that of any other while program. I'm not going to be talking about recursive programs in this talk. So here, these programs have assignments. So x is assigned y, x is assigned f of z1 through zk. So the function f is an uninterpreted function. We have conditionals, we have loops. And the conditions inside the conditionals are essentially Boolean combinations of equality atoms or relational atoms. And the postconditions are again Boolean combinations of equality atoms or relation atoms. And in general, we can always model relations as functions. So in the rest of the talk, I'll also not be talking about any relations. The verification problem for such programs is the following. So if you have a program P and a postcondition phi, the program P satisfies the postcondition phi if it is the case that for every data model, so recall that a data model comes with its interpretations of the functions and the constants. So it asks us if it's the case that for every data model and for every execution that is feasible in the data model, the postcondition phi is true in that model at the end of the execution. So let's look at this example. This example searches for a key k in the list segment that starts from x and ends at y. And when it finds the key, it turns a Boolean flag b to be true. So the next pointer is modeled using the function n, and the key field is modeled using the function key. and the postcondition says if B is true, then the pointer R, the key at the pointer R is K. So it so turns out that if you model this program as an uninterpreted program, you can still verify it. So if you treat this program as an uninterpreted program, which means that I'm going to treat the function key as an uninterpreted function, and the same for the function n, then the verification question essentially becomes to check if for all interpretations of the functions n and for the functions key, and for all the initial values of x, y, b, r, and k, these are the program variables, check whether the following formula holds at the end of every execution. So it turns out that this program is a coherent program, so which I'm going to talk about shortly. And this class of programs are decidable, and therefore we can verify this program without the use of any loop invariants. So let's look at executions of uninterpreted programs, and this is sort of essential to understand coherence. Executions of such programs are essentially sequences of basic statements. So basic statements are assignments or assumptions, and all other statements essentially compile down to these two kinds of statements. With every execution, we can associate an algebraic view. By that, I mean an execution computes terms using the constants and the function symbols in your program, and also accumulate assumptions or constraints on these terms. So let's look at this view in a bit more detail using an example. We have the same example on the left. And to begin with, each of the variables store terms. So these terms are uninterpreted constants. So for example, the variable y stores the constant y0. The variable x stores the constant x0. The variable k stores the constant k0. And let's say the first step is the assumption, assume t equal to f, t not equal to f. And this gives rise to this ground atom t0 not equal to f0. If you look at this, the next step is this assignment b f to b, and that means the term stored in b is now f0. And as you proceed, you accumulate more constraints. So at this point, what is happening is that a new term is being computed. So key of x0 is the new term, and now the variable d points to this term. So again, if you continue doing this execution, you compute new and new terms, and you also accumulate constraints. So this is what the picture looks like at the end. So with this algebraic view in mind, let's look at coherence. So we say that a program execution is coherent if it satisfies these two properties. The first property is called memoizing, and the second property is called early assumes. And intuitively, the memoizing property says that you're not allowed to recompute terms. Or rather, if you're recomputing a term, then some variable in your program already stores that term at the point of recomputation. And the second property, early assume, says that whenever you encounter an assumption in your an equality assumption in your execution, then that assumption is in some sense early. And let me get back to the detailed definition. So formally, the memoizing property says that if you have an execution of the form sigma followed by the assignment f of y bar to x, so let's say the term corresponding to f of y bar is t, and let's say sigma already had computed this term before. Then if that happens, then the memoizing requirement says that there should be some variable that already stores t at this point. So essentially, you are not recomputing terms, or rather, if you're recomputing terms, you're keeping track of those. When you have equality assumptions, this is more subtle, and you also have to account for equivalent terms that might have been computed before. Okay, so this example again is such that all its executions are memoizing. And that's because it's a single pass algorithm on the list. And what is happening is that you're computing terms like x and n of x and n of x, or key of n of x, etc. And you're really never recomputing any term again. And that means this program is such that all its executions are memoizing. In fact, if we had a 2-pass algorithm, then that will not be such that its executions are memoizing, because you'll be recomputing terms and you will not have enough variables to store those terms. So let's look at the second requirement, early assumes. It says that formally, if you have an execution of the form sigma followed by assume x equal to y, and if it so happens that there was a super term of the term stored in x or y, that the execution would have already computed before this point. If that happens, then the early assumes requirement says that there is a variable that keeps track of this super term. Okay, so now let's look at the main result of the paper. A program is coherent if all its executions are coherent. And the main result of the paper is that verification of coherent programs is decidable. It is PSPACE complete when you do not have recursive function calls, and in the presence of recursive function calls, it is X-time complete. So notice that this complexity is the same as that of Boolean programs. As before, to the best of our knowledge, we show that this is the first class of programs that work over infinite domains and yet admit decidable verification. And further, in the paper, we show that if you relax either the memoizing requirement or the early assumes requirement, then the kind of programs that you get do not admit decidable verification. So let's look at the key ideas in the algorithm. We'll not go into a lot of details because it's involved, and you're welcome to look at the paper for the details. So the key idea is called streaming congruence closure. So it's an algorithm that analyzes executions, and is such that it only requires constant memory. It's a constant memory streaming algorithm. And roughly, it maintains the congruence closure of the set of terms corresponding to the variables at any point in the execution. And that means you do not have to keep track of the terms that were computed but are no longer in any variable. And therefore, it's constant memory. And of course, coherence is the key requirement that makes this algorithm possible. In fact, coherence can be thought of as related to this graph theoretic notion called path decomposition. In fact, when an execution is coherent, its path decomposition has a bounded width. So now that we have a constant memory algorithm for analyzing executions, we can come up with an automaton that accepts coherent executions that do not satisfy a given postcondition phi. So the states of this automaton are triples of the form tilde dp. The first component tilde essentially summarizes the equality relationships between the variables. So something like x is equal to y, w is equal to z, etc. And this is essentially the congruence closure of the equality assumptions seen in the execution so far. The second component d accumulates essentially the disequalities seen so far. So x is not equal to w, y is not equal to z. And the third component tells you what are the functional relationships between the variables. So something like the variable b is equal to f of the variable a, or x is equal to g of a comma y. So f and g are uninterpreted functions in your programs. The verification question, therefore, boils down to a language theoretical question. The postcondition phi holds in the program P if and only if all the executions of P are disjoint from the language of the automaton. And for while loops, both these executions, for programs with while loops, both these sets are regular sets, and therefore this question is decidable. And for when you have recursive function calls, both these sets are visibly pushed down languages, and then again decidable. So in our paper, we also show that if you're given an uninterpreted program, you can also check if it is coherent, and this problem is decidable. Let's move on to the next contribution, k-coherence. So this program on the left is not a coherent program. What is happening here is that you're computing n of x and storing it in y, and then you're overwriting it to some other value. And now at this point, you're computing n of x again, and that means you're recomputing, but you do not really have the same term again, and that breaks the memoizing requirement. So this is not a coherent program, but you can make it coherent. You can add an additional variable g, and whenever you are, before you overwrite a term, you store it in g. So g here is a variable that does not affect the semantics of the program. It's always only a write-only variable. You never read from it. And because you can add one variable to the first program and make it coherent, we said that the first program is one coherent. In general, a program is k-coherent, where k is a natural number. If you can add k many ghost variables, these are these additional auxiliary variables, and make it coherent. So in our paper, we show that the problem of checking if a program is k-coherent for a given k, this problem is decidable. And in fact, we can also verify k-coherent programs in the same complexity as that of coherent programs. So to conclude, we introduce a new class of programs called coherent and k-coherent programs, and we show that verification is decidable. It is indeed, to the best of our knowledge, the first natural class of programs that work on infinite domains and yet admit decidability. In fact, the decision procedure is as efficient as that of Boolean programs, so PSPACE for programs that do not have recursion and X-time otherwise. And there are lots of avenues for future work, including evaluation of this technique as a practical program verifier. In fact, some days back in VMCI, there was a paper called Euphoria, wherein they showed that when you treat programs as uninterpreted programs, you can prove a lot of programs to be correct with this abstraction. We'd also like to see if we can extend our results to the case when functions may not be completely uninterpreted, but constrained by some theories or axioms. So something like if you have a relation which is transitive or a total order, then we'd like to see if the assumptions of coherence give you decidability. More generally, there are more automata theoretic techniques like trace abstraction due to Heisman et al. That are effective in proving programs correct. And we'd like to see if the assumptions of coherence enrich the kind of programs that you can prove correct. So overall, we are very excited about this result, and we believe that this opens up a lot of new research questions for the programming languages community. Thank you.
So we did have a question in Slido, but you answered it later in the talk, and so it was withdrawn. Do we have any questions from the audience?
Thanks. You said that you can verify programs without needing loop invariants, but do you think from your technique you can also maybe extract loop invariants for interpreted programs?
Yes, that's true. We can extract loop invariants which essentially look like disjunctions of equalities and disequalities of the variables at any point. Yeah, so that's indeed possible.
When you say recursive program, assume you have local procedures, global variable, you pass procedures as parameters, you have a block structure plus maybe other condition, then you can simulate a Turing machine on the stack, and so even if all data are Boolean, it's not decidable. So I think you must put restriction of what you call recursive programs.
Okay. So I think I want to listen to the question again.
Repeat the question.
I can answer.
Sure.
So here the recursion is only where you don't pass procedures as parameters, but you only pass data as parameters. You can only pass variables or terms you've computed, not procedures.
It seems that coherence restricts a lot of classes of programs that you can verify. Can you comment on which case studies have been able to apply your research?
So as such, right now we do not have any case studies, but we believe that it's definitely, if you have programs that, for example, do 2 passes over some data structures, then those may not be coherent programs. On that note, we also think that you can also analyze non-coherent programs, and by that I mean if you get an answer that says, if a technique say that the program is indeed correct, then it might mean that the program is indeed correct. So it's a sound abstraction. Yeah.
So I mean, so you are very fond this problem of P implies phi, but why you do not have a precondition? Somehow it's whole triple. You have both precondition and postcondition.
It's the whole triple true P phi. Yeah, I'm sorry for the strange notation.
So you mean you have precondition or?
It's true.
Okay.
So any precondition can be done by just an assumed statements in the beginning of the program. So.
I think that's the last question we have time for, so let's thank the speaker.